Let's say we have an electron that we start on this plate of a capacitor. It starts at rest on this plate. What's going to happen to the electron if we let go of it?
It's going to stay where it is.
Oh, yeah, I didn't want it to do that. All right, let's try again. Yeah, we'll stay where it is. Good answer. How about this capacitor? What will happen to this electron if we let go of it?
So it moves the other side.
Right. So what happens to its kinetic energy over the course of this experiment?
Increases.
Yeah. I'm sorry?
But does it stop? Is it slow down before? Does it stop at the other side?
Let's actually suppose there's a little slit here, so the electron can just go shooting straight through.
Okay.
And let's say that for one reason or another, it's going to keep passing right on through, and it's not going to be attracted by these positive charges on the other side. It's somehow just going to keep going straight through. So this is just a device for accelerating this electron. This is a device for accelerating this electron. In fact, the best way to think of it is there's two slits. You start with an electron here that's basically at rest, and then you put it inside the first slit, and it gets accelerated to here, and then it just keeps on going out forever. For some reason, these positive charges don't affect it anymore when it gets over here. There's some kind of barrier or something. Okay. All right, so its kinetic energy is going from 0 to something. Here the kinetic energy was, say, 0 electron volts, and here the kinetic energy might be, I don't know, say 10 electron volts. So the change in its kinetic energy was 10 electron volts. Where did it get that energy? Energy can't come from nowhere.
The energy that was stored, keeping it with the negatives.
That's right. So what happened is it must have been using up its potential energy. So what's the change in its potential energy?
Negative.
That's right. That's conservation of energy. If it gained 10 electron volts of kinetic energy, it must have lost 10 electron volts of potential. Its potential energy here decreased. After all, is the electron moving where it wants to go or where it doesn't want to go?
Where it does.
If moving where it wants to go, and that lowers your potential energy. Remember, anytime you're going someplace where you're happy, that gives you a lower potential energy. That's going to be an important idea still in this point of the course. Things want to have low potential energy. If you're moving where you want to go, that means you're lowering your potential energy. Okay, but that gives us a very important idea, which is in magnitudes, the two changes have to be equal, because any energy that you're losing from potential energy is being gained for kinetic. Okay, and you know I like to use the dots for magnitudes. So these are not equal in signs. One is positive and one is negative, but very often we've seen the equations work better if you work with magnitudes. So with magnitudes, these are the same, so we'll put in the dots for that. So in this kind of simple example, whatever energy you are losing potentially goes into your kinetic. Or if we were moving in the other direction, we would be losing kinetic energy and storing it as potential energy.
Or if you're still moving in that direction, aren't you moving still?
Suppose we start with an electron that's moving in this direction, and suppose that this device is designed so that it's, by the end, it's going to have completely come to a halt. Well, it doesn't even matter if it's completely come to a halt or not. Anyway, the point is, as it moves through here, it's going to get slowed down, right? Well, whatever energy it loses kinetically is getting put into its potential energy. Okay. So it doesn't matter whether it comes to a halt or not. The change in kinetic will equal the change in potential in magnitude, because we have conservation of energy. Any energy that we're losing kinetically is going to be stored as potential, or any energy that we're gaining kinetically is coming out of our potential. Again, and as usual, it's most useful to use the dots to just focus on magnitudes. In magnitudes, these changes have to be the same. So, unfortunately, I'm running out of room here, but now, moving down, I guess you have more room in your flowchart, we can figure out how to find the potential energy.
So you just say it's the same magnitude.
So I'll just write that formula we were just talking about next to this arrow. If you know how the kinetic energy is changing, then you know how the potential energy is changing. All right, now this is a capacitor. We know that we usually talk about the voltage across a capacitor, or the potential difference across a capacitor. Potential difference. When you're ready, what's the SI unit for potential difference?
V. I mean, it's a volt.
Right.
So that potential energy is the same as electric potential energy, kind of?
Yeah. So this potential energy is short for electric potential energy. And this potential difference is short for electric potential difference. The key difference is if you use the word energy, you mean U. But if you use just the word potential, you mean V. Potential by itself means V, and potential energy or energy means U. Again, it's too bad they use names that are so similar to each other, but the crucial thing is whether you mention energy or not. Without the word energy, it's just the potential or the potential difference, which is V.
So you use V as U over Q?
Good. All right, that's good. That's something we saw a long ways back. That's good that you're remembering that. So I'm going to write that like this. The change in energy is Q times delta V. Since after all, what are the units for Q?
Coulombs.
And what are the units for delta V?
Joules per coulomb.
And that gives us joules, which are the appropriate units for energy. If you know the units, you should be able to come up with the formula. Or if you know the formula, you should be able to come up with the units. So yeah, what are the units here? Volts, which are joules per coulomb. All right, I think that's the end of our flowchart here. All right, so that's this flowchart. These are really pretty important concepts here. Now, one thing to notice here is then we have two different flowcharts, and one of the big things that messes people up is they use this chart when they should be using this one, or they use this chart when they should be using this one. If you're working with light and electromagnetic radiation, then you would use this top flowchart. If you're working with light and EM radiation, which is photons, you would use this top flowchart. But if you're working with anything else, particles with mass, you use the bottom flowchart. Usually this is for electrons, but it would work for other things as well.
For light or EM.
That's the top flowchart. Remember, light is just a type of EM radiation. Okay. And you can see how it's easy to get them confused because they both tell you how to go between wavelength and energy. Here's wavelength and energy using E equals HF. And here's a completely different way to go between wavelength and energy. Remember when we're talking about particles, when they talk about the energy of a particle, if they don't explain, they usually mean the kinetic energy of the particle.
So is there a difference between the kinetic energy and then the energy that's in the top one?
Yeah, I'm not quite sure how to think about that myself. I'm not sure exactly what type of energy you would think of this of. I guess you would think of this as kinetic energy. I'm not quite sure how to think about that type of energy there. Usually we don't really classify photons into kinetic or potential. We just call it the energy. I'm not quite sure what the right way is to think about that. But for particles with mass, it helps to sometimes think about kinetic or potential.